So it's time we have a little conversation about the words must and could, which it turns out are kind of big deals on the test. Must translates into at least. It means to minimize or restrict. It works like this. Let's say that you wanted to buy a house, so you go to the bank to get a mortgage, and the bank says, okay, we'll lend you the money, but you must make at least $150,000 a year to qualify for the loan. So if you get that loan, then we know for sure one thing about you. You must make at least $150,000 a year. Now the word could is the opposite of the word must. It means to maximize or expand. So if you get that loan, we know that you must make $150,000 a year, but you could make $1 million a year. You could make $2 million a year. We just don't know. The wording of the question doesn't put a ceiling on that. Now these words, must and could, do come up quite a bit on the test, so let's take a look at how they work on actual questions. Okay, let's take a closer look at how must and could work. Now we're going to run through some drills. These aren't going to be like normal test questions, but they're going to be very helpful in kind of teasing out these concepts so that you can use them effectively on the test. Okay, so if 3n over 45 is an integer, must n over 15 be an integer? Now what does that mean? It means when we load up n with as little DNA as possible. Remember, must means minimize. So we want to give n as little DNA as we possibly can. Does n still contain all the DNA of 15? Well, let's find out. 3n over 45 equals an integer literally means that 3n must contain the DNA of 45, so we know that 3n contains 3 squared times 5. Now, n alone, though, must contain a 3 and a 5. And why is that? Well, n doesn't have to contain both 3's because n has a 3 helping it out in the numerator like this. So in the numerator, we have 3 times n, and then in the denominator, we have 3 times 3 times 5, which is 45. Well, 3's cancel. Now the n alone has to cover off on the 3 and the 5. That means n must have a 3 and a 5 in it. Could n have a lot more DNA in it? Sure, but it must have a 3 and a 5 in it. Must n over 15 be an integer? Yes, it must, because when we minimize the amount of DNA that n must have, it still had a 3 and a 5. Let's take a look at another example. 7n over 24 equals an integer. Must n over 24 equal an integer? Again, the word must means we want to minimize the amount of DNA that's in n. We want to make it as small as possible. All right, well, let's see what we get. 7n over 24 equals an integer means 7n must contain the DNA of 24, so 7n must have 3 2's in it and a 3. Now, n all on its own actually must contain all of that DNA. N must contain 2 3's and a 3, and why is that? Well, the deal is that, yeah, n has a buddy. It has a 7 up there in the numerator, but the 7 isn't helping. The 7 doesn't cross off anything in the denominator, so the n all on its own has to contain all the DNA of 24. N must contain 3 2's and a 3. Could n contain a lot more? Sure. N could be a huge number. Must it? No. It must contain 2 times 2 times 2 times 3. Must n over 24 be an integer? Yeah, it has to be. Let's take a look at another one. 3n over 24 equals an integer. Is n over 24 an integer? Okay, well, let's take a look at this, and notice we've got the word is and not the word must. We'll cross that bridge when we come to it, but we know that 3n over 24 equals an integer means that 3n must contain the DNA of 24. 3n must contain 3 2's and a 3. Now that means n must contain 3 2's. N doesn't have to contain that 3 because in the numerator, n's got a helper. N's got a 3 in the numerator, and that can cross off one piece of the DNA in the denominator, so n, all on its own, has to take care of those 3 2's. So at the very minimum, n's got to contain 2 times 2 times 2. Could n be a bigger number? Sure, but it must contain 3 2's. So now let's go back and look at the wording of what we're asked. Is n over 24 an integer? Well, you could say, no, you know what? Because n could totally be 8. But hang on just a second. Yes, because n could be a big number. N could be like 24,000. So the answer is we don't know. Maybe. We don't have enough information to answer the question. All right, nice job. Let's take a look at another one. If 27 is a factor of 3x, does 9x have to be a multiple of 108? Okay, well, let's take a look at the language, because if there's one thing we've learned, most of this test is about the language. What we're really being asked is if 3x over 27 is an integer, remember, factor means small number, so 27 is a small number, 3x is the big number. Does 9x have to be a multiple of 108? Means 9x over 108 is an integer, because remember, multiple means big number, so 9x is on the top, 108 is on the bottom. All right, well, let's find out. Now, 3x must contain all the DNA of 27, or 3x contains at least 3 3's. Could 3x contain a lot more than 3 3's? Yeah, but it has to contain at least that. It must contain 3 3's. Okay, so we're asked, is 9x over 108 an integer? Well, that's the same as 3 times 3x over 108. Is that an integer? Well, okay, well, let's take a look at this 3x business. Do we want to load up 3x with as much DNA as we possibly can, or with as little DNA as we possibly can? Well, we have the word have, so we want 3x to have as little DNA in it as possible. So we're going to replace 3x with 3 times 3 times 3, which means on our numerator we get 3 times 3 times 3 times 3, that's our 3x, over 108. Is that an integer? Hey, you know what? I don't think it is, because that denominator, 108, that thing is even. We know for sure 108 has a 2 in it. Are there any 2's in the numerator? There are not. Will that numerator ever cancel off on all the DNA of the denominator? It will not. Not as long as 3x has the minimum amount of DNA. That numerator will only have 3's in it. So we know for sure that 9x is not a multiple of 108, because 9x does not have to contain a 2. Okay, good job. Let's take a look at one more that is more of an actual test question. If n is a positive integer and n squared is divisible by 54, what is the largest integer that must divide n? What is it exactly that we're being asked? I think we're being asked something like this. So n is a number, and we're being asked, what is the biggest number that will divide into n? And everything we're dealing with here is integers. Okay, so what are we told? We're told that n squared is divisible by 54, and that means that n squared over 54 is an integer. And at this point, you might be tempted to take the square root of each of these numbers. Don't be fooled. That's what the test wants you to do. You're seeing the word divisible, divide. You're seeing the word integer. You can look at that and know for certainty that you are in a number properties question. So we want to use number property tools to answer this. Because the truth is, if you start taking the square root of n squared and 54, you're going to find the square root of 54 isn't an integer, and you're going to get stuck. So instead, how we want to think about this is we know that n squared must contain all the DNA of 54. N squared's got to contain 1, 2, and 3 3's. Are we being asked about n squared? No, of course not. We are being asked about n. So what do we know about n? Well, we're kind of given a rule, like n could be anything, but you know what? When you square n, you must get at least 2 times 3 cubed, because we know that n squared contains at least 2 times 3 cubed. So I'm thinking n's got to have 2's and 3's in it, right? Because when we square it, I end up with a bunch of 2's and 3's. So what could n be? Well, could n be 6? I don't know, let's try it and see what happens when n is 6. So if n is 6, then n is 2 times 3. Now, if we square 2 times 3, we get 2 squared times 3 squared. Now, is that enough DNA? Well, what are we looking for in terms of DNA when we square it? We need 2 times 3 cubed. We have enough 2's. We don't have enough 3's. We only have 2 3's. We need 3 3's. N can't be 2 times 3. We don't have enough 3's. I think we need to add another 3 to our n. So instead of making n 6, 2 times 3, let's make n 2 times 3 times 3. Now if we square that, we get 2 squared times 3 to the 4th. And is that enough DNA? Yeah, it sure is. Our job was to square n and get at least 1, 2, and 3 3's. We did that. And that is the smallest number n can be. 18 is the smallest number n can be, because if we take away any DNA from n, when we square it, we won't get enough 2's and enough 3's. The smallest number n can be is 2 times 3 times 3, which is 18. Okay, well now let's look at our answer choices. Now that we know what n must be, we need the biggest integer that must divide n. Well, let's take a look at A. So does 1 divide into n? Yeah, 1 totally divides into 18. But is it the largest integer that divides into 18? No, it's not. Does 6 divide into our n? Does 6 divide into 18? Yeah, sure it does. Is it the biggest number that'll do it? No, it's not. What about 9? Does 9 divide into 18? You bet it does. Is it the biggest number that'll divide into 18? No, it's not. There's one bigger number. 18. Does 18 divide into 18? You bet it does. It absolutely does. Is that the biggest number that will divide into our n? Yeah, it is. 18 is the biggest one that must do it. Now, is it possible that n is a huge number? Yeah, it is. But we have the word must, which means that we're trying to make our n as small as we possibly can. That means our n, we want to assume that our n is 18. Okay, that's a tricky one. Definitely go through that one a few times. It's also explained again in the companion guide. If you can get your head around this one, you can basically handle any kind of DNA, must, could kind of stuff. So really, really nice job.